Okay, so in this next section, next session, we'll continue with the Bayes rule. Okay, so we had seen how the Bayes rule is useful, and we'll now see how you combine evidences. So suppose we have two or more pieces of evidence. Okay, for example, P cavity given toothache and catch, right. So, if you have something like this, if you have the full joint distribution, you can just get this information from there. Okay. So, if you go to that full joint distribution table, since all the values are there, we need to see toothache and catch, right. So, let me go back and show you that. Okay. So, you have to say toothache and catch, right, and so these two values is what you have to use, 0.108 and 0.016, right. Yeah. So, that gives you your probabilities that you are actually looking for. Okay. So, suppose you use a Bayes rule. Okay. So, probability of cavity given toothache and catch will be probability of toothache and catch given cavity into P of cavity. Okay. So, you need to know the conditional probability of toothache and catch, right. So, so what happens is that so if you have two evidence variables, okay, then it may be easy to do this, but if there are a lot of them, okay, for example, if you have n possible evidence variables, X-ray, diet, oral hygiene, etc., there will be 2 to the power of n possible combinations. Okay. So, then that will be difficult to actually do, right. So, you need to have the notion of independence here also. Okay. So, suppose you have these evidences that you are using, if they are all independent of each other, okay, then you have what is called the conditional independence. Okay. So, if you have conditional independence, okay, so probability of toothache and catch given cavity can be written as probability of toothache given cavity, probability of catch given cavity. Okay, so, this is what is called the conditional independence. So, if conditional independence can be found, then it makes it easy to solve this. Okay, you can write this whole thing as alpha into probability of toothache given cavity, probability of catch given cavity into probability of cavity, which makes it easier to use this. Okay. So, how do we write this definition for conditional equivalence? Okay. So, the probability of x and y given z is probability of x given z and probability of y given z, right. So, that is what is called the conditional probability. So, if we have P toothache and catch given cavity, we can have probability of toothache given cavity into probability of catch given cavity if they are conditionally independent. Okay. Okay. So, you can get a decomposition in this way. Probability of toothache catch cavity is equal to probability of toothache catch given cavity into P of cavity, right. And we can write this as probability of toothache given cavity P of catch given cavity into P of cavity. So, you can bring it down to this form. Okay. So, what happens is that the original table had 2 to the power of 3, that is 8 entries, okay, but here there will be a reduction to some extent. Okay. So, you find that the smaller table has 5 independent numbers as compared to the other one. So, you may find it is not really that much reduction, but what you have to see is that you are looking at something like n symptoms, right. So, n is quite large. Okay. So, when you have n to be quite large, you find that the size of the representation grows as order of n as n increases and not order of 2 to the power of n. So, it makes a difference when you use that. Okay. Conditional independence assertions can allow probabilistic systems to scale up, okay, and in the sense that you can work with more number of variables because you have conditional independence, right. So, if you say cavity separates toothache and catch, okay, it is the cause of both of them, okay, but then toothache and catch are independent of each other, that is what you can say. So, you can write the full joint distribution as follows. So, cause effect 1 to effect n, you can say p cause into p effect I by cause. Okay. So, this is what is the naive Bayes model, which is used as a classifier, naive Bayes classifier, right. So, you are assuming that all these effects are independent of each other basically, and it is found to work really well in many cases, right. Okay, so, now we will talk about the Bayesian network. So, what you are doing in Bayesian network is you are actually seeing which variables are independent of which variable and which variable is dependent on which variable, because you will find that not every variable is dependent on every other variable, right. When you do the full joint probability, you are assuming that every variable is dependent on every other variable, okay, but that is not true, right. So, what you do is that you form what is called the Bayesian network. So, what do you do? The specification of that is as follows. So, you take the node corresponds to a random variable, okay, which may be discrete or continuous, and you have a set of links or arrows connecting pairs of nodes. Okay. So, suppose if you have an arrow which goes from node x to node y, it means that node x influences node y, or node x is the parent of node y, right. So, node y is dependent on node x, right. So, this type of a graph, whatever you are getting, it does not have any directed cycles. So, you can say it is a directed acyclic graph, right. It is directed, but there are no cycles basically. Okay. And each node x I has what is called the conditional probability distribution, okay, which is there in the conditional probability table. Okay. So, the probability of a node x I is conditioned on its parents, right, and you are saying that all these, if you have a parent and you have more than one node, okay, like p x I, you find that you are assuming that they are independent of each other. Okay. So, what does the arrow mean? It means x has a direct influence on y. Okay. So, it is called the parent of y basically. So, you can get the topology of the network in this way, and for each node you need to find the conditional probability distribution, right. It is called the conditional probability table. Okay. So, here we have the Bayesian network for this small 4 values that we have, right. So, you have weather, cavity, toothache and catch. So, here we can see that weather is independent of the other variables, it does not have any incoming nodes or outgoing nodes. And then we have toothache and catch, which is dependent on the cavity. So, cavity is the parent node and you have toothache and catch which are dependent on that. But toothache and catch, even though they are both have cavity as the parent, they are conditionally independent of each other. Okay. So, that is the thing. Given cavity, they are both conditionally independent. So, this is a very simple Bayesian network. So, we will talk about a slightly more complicated example, right. So, what we have here is that you have a new burglar alarm installed at home. So, this is what is found in Russell and Norvig basically. It is fairly reliable at detecting a burglary, but also responds on occasion to minor earthquakes. You also have two neighbors, John and Mary, who have promised to call you at work when they hear the alarm. John nearly always calls when he hears the alarm, but sometimes confuses the telephone ringing with the alarm and calls then too. Mary on the other hand likes rather loud music and often misses the alarm altogether. So, this is the what we are trying to see and make a Bayesian network for this. So, given the evidence of who has or has not called, we would like to estimate the probability of a burglary. So, that is the problem we have. So, this actually is the Bayesian network which is used here. So, we have we have chosen 5 variables here: burglary, earthquake, alarm, John calls and Mary calls, right. So, burglary and earthquake are basically do not have any incoming nodes, okay. So, they are not influenced by any incoming nodes. Then you have the alarm, and the alarm is influenced by the burglary as well as by the earthquake, like we saw, right, because it says it also responds on occasion to minor earthquakes, right. So, both these are incoming nodes to the alarm, and John calls and Mary calls depends on the alarm, right. So, this is the network that we have, right, and we need to have the conditional probability table at each node here. Okay. So, if we consider the conditional probability table for John calls, what we want is probability of John calls given the alarm, right. So, alarm can be either true or false. So, if the alarm is true, if the alarm is false, then what is the probability of John calls, right. You can also have the probability not P of j, right, but you find that these two are add up to 1. So, there is no need of having the other value in this particular row, right. Similarly, Mary calls, okay, you can have these values. Then you come to alarm. So, alarm has 2 parent nodes, right. So, you have B and E, that is the burglary and earthquake, and there are 4 different possibilities of this. Both can be true, or one of them can be true, or both of them can be false. So, you have these probabilities given here, right. And then you have the earthquake and burglary, they do not have any incoming nodes. So, you have only probability of burglary and probability of earthquake, and not probability of not B, which will be 1 minus this, and probability of not E, which will be 1 minus this basically. So, this is what is called the Bayesian network. So, we can see from the network structure that burglary and earthquake directly affect the probability of alarms going off, but whether John and Mary call depends only on the alarm. Okay. And then we have the conditional probability table, right. So, there are many other things, for example, Mary's current listening to loud music or to the telephone ringing, etc. So, these factors are just added into the system using just these 5 variables, right. The you need, I mean, it is just to reduce, you need to do a lot of work to add all those things, and you may not have all the values, and anyway it is going to be approximate. So, just using these 5 values is enough to form this Bayesian network. Okay, so let us look at the Bayesian network, right. So, if you look at the Bayesian network, okay, if you look at the full joint distribution, okay, the full joint distribution assumes every node is affected by every other node, influenced by every other node. But here we know that the node is only influenced by the parents of the node, right. So, because of that you can reduce the complexity that you are basically working on. Okay. Okay, so what we can say is that how do we find any probability that we want using this Bayesian network that we are talking about. Okay, suppose we want to calculate the probability that the alarm has sounded, but neither a burglary nor an earthquake has occurred, and both John and Mary call, right. So, what do we want? We want the probability of John calls, Mary calls, alarm, okay, not B and not E. Okay, so, how do we find this? What we need to do is we know that probability of John calls depends on the alarm. So, we can say probability of John calls given alarm, probability of Mary calls given alarm, probability of alarm given, we know that both B and E are not there. So, not B and not E, and probability of not B and probability of not E. Now, if you look at all these values are available in your Bayesian network, right. So, if we take this Bayesian network, all those values are available in these conditional probability tables that you have here. Okay. So, we have probability of not B, which is 1 minus this, probability of not E, which is 1 minus this, probability of John calls given alarm, right, which is 0.9, probability of Mary calls given alarm, which is 0.7, and here probability of alarm given both are false, that is 0.001, right. So, you can use all these values, okay, put all these values here and you can get the probability of this. So, what we have found is probability that the alarm has sounded, but neither a burglary nor an earthquake has occurred, and both John and Mary call. Okay. So, this is the probability that we are using. Even if you use your full joint distribution, you will get the same answer, right. And you can use your Bayesian network, which makes it easier basically. Okay, now how do we construct this Bayesian network, right. So, if we rewrite the entries in the joint distribution in terms of conditional probabilities, we can write it in this way: probability of x 1 to x n, that is the variables, to be x n given x n minus 1 up to x 1, okay. And then we can reduce it further and you will get this as the chain rule, right. So, what we can do is, this is equivalent to the assertion that P of x I given x I minus 1 up to x 1 is equal to probability of xi given parents of xi, right. So, what you do is that what you need to do is you need to do the what is given here. First you need to find the ordering of the nodes, right. So, how do you order the nodes? You find the node which does not have, which is not influenced by any node, right. So, you can start with those nodes, and from those nodes you can see the nodes which those nodes influence, etc. So, you find the ordering of all the variables that you have. Okay, first determine the set of variables that are required and order them. Okay. Any order will work, but the resulting network will be more compact if the variables are ordered such that the causes precede the effects. Okay. So, the one which does not have any causes, for example, earthquake, those can come first basically. Okay. And for each one, what do you do? You find the minimal set of parents for them. Okay. And for each parent, insert a link from the parent to xi, and you write the conditional probability table for every variable. So, all the 1 to n variables, for each of them you do this thing. Okay. You find the parents and write the conditional probability distribution and put a link between the node and the parents. So, that is how you are going to do this. Okay. So, the next thing that we need to worry about is compactness, or the ordering of the nodes, right. Actually, you can order the nodes in any way that you want, right. So, for example, we can see an ordering here, right. So, suppose I take the ordering, okay. Okay. So, suppose we take Bayesian network, okay. And suppose each random variable is influenced by k others. Okay. So, if they are influenced by k others and there are n Boolean variables, then the complete network can be specified by n 2 to the power of k numbers, right. And the joint distribution is 2 to the power of n numbers, right. So, there is a difference there. Suppose we have n as 30 and you have k is equal to 5, you find that the Bayesian network requires 960 numbers and the full joint distribution requires over a billion. Okay. So, it makes a lot of difference if you are able to use the Bayesian network instead of using the full joint distribution. Okay. Okay. So, suppose we use a different ordering of the nodes, right. Suppose we use the order Mary calls, John calls, alarm, burglary and earthquake. Then what happens, adding Mary calls, you won't have any parents for that, right, because you are going to put in this particular order. Adding John calls, if Mary calls, then probably means the alarm has gone off, which of course would make it more likely that John calls. Therefore, John calls needs Mary calls as a parent, etc. Right. So, if you are going to go through all these things in this particular order, what you are going to get is this Bayesian network, which makes things a little more complicated than what we had in the previous case. Okay. And the worst that you can get, okay, is if we put it in this order: Mary calls, John calls, earthquake, burglary and alarm. Okay. You are going to get this very complicated Bayesian network. So, the ordering of the nodes actually makes a difference, right. So, if you can order the nodes, like we said, you start with nodes which do not have any causes and then go down, etc. You will find that the ordering of the nodes actually leads to compactness, and that compactness will help you be able to do things much faster. Okay. Okay. So, this is the basic Bayesian network that we can talk about, and we have seen how you can get a combination of any probabilities put together, right. So, you can get a joint probability of different variables in that 1 to n that you are looking for. So, we will stop here at this session, and we will continue in the next session, where we will talk about how things change over time. Okay. So, when it changes over time, how do you change your Bayesian network over time to get the probabilities that you are looking for. So, we will stop here.